So essentially, a general double integral in terms of x and y over some region D or R it can be transformed into an equivalent double integral over the same region, but essentially using R's and Th's. And the things that we do to convert is every x can be turned into this, every y can be turned into this. But if you see any x squareds and y squareds around, you can actually save some time and turn it into this. And the weirdest part is that the dA, which would be what, dx, dy, whatever, gets turned into R. That R is important, dr, d theta. So I've got one set up here. The sine of x squared plus y squared dA, the region R is in the first quadrant and it's bounded by two circles. So since it's in the first quadrant, it's here. And can you imagine that's a circle radius 2 and that's a circle radius 3. So that is your region R. So we need to describe R in terms of polar. And in this case, R goes starts at 2 and finishes at 3. And theta starts at 0 and swings up to pi upon 2. Are we comfortable about how this becomes this picture and then you use the picture to define the region in terms of R's and thetas? We good with that? Then we are good with that. So what we're now going to do is we're going to start putting this thing together. R equals 2 to R equals 3. Theta equals 0 to theta equals pi upon 2. The sine of x squared y squared becomes the sine of r squared because of this. The r, whoops, where is the r dr d theta? I'm going to stick the r there. I'm going to do dr and then I'm going to do d theta. And if we're really lucky, the integral that we now have will be easier to do. And secondly, it could even be variable separable, which tends to make your life even easier. Can this one be separated?
There's no theta, so there's really no need, right?
Well, I guess there's no need, but you could still separate it, but just having a one of it.
So my understanding is that you take the integral, the double integral of sine x squared plus y squared dA, and you rewrite it in terms of r's and thetas?
Yeah.
Okay.
Yes. Now, you're quite right. Since there's no thetas, I could just do this integral, you know, this guy, and then do it with that. But if I do it this way, I don't know, it's just appealing. It just looks better. Why do I like it? Because aren't these both just calc 2 integrals? This one here is just integral of 1. I wouldn't even really need to do any work. Are you happy why the answer's pi upon 2 without me even doing work? The integral of 1 from 0 to pi upon 2 would eventually get you pi upon 2. How am I going to tackle this guy?
Isn't that your standard chain rule?
I agree.
Well, we're integrating, so we don't really have a chain rule in integration. So I'm not sure if that's just the wrong label you gave to me.
U sub.
U sub, yeah. That's an r squared, that's an r. Now, if it would r sine r, it would have probably, wouldn't have probably, it would have been integration by parts. But it's going to be a u sub using r squared. So this integral now essentially becomes an r, a sine u, a 1 over 2r du. This cancel, and we get the integral of a half sine u du, which in turn becomes negative 1/2 cosine u. And then turn, in this case, back into r's and evaluate it from r equals 2 to r equals 3. And since I'm running short of room, if you plug in 3 here, you get 9. If you plug in 2 here, you get 4. So you end up with negative 1/2 cosine 9, take away negative, add 1/2 the cosine 4, and it's okay to be ugly because that's the exact answer, and 9 and 4 are considered okay forms for the result. Okay. Well, let's return back to the original question. If you try to do this integral, let's do it in red. If you try to do this integral with respect to x and y, and it doesn't matter which one you do first, what's the antiderivative of sine x squared plus y squared with respect to x? Well, the answer is we don't know. You know, there are many integrals that you cannot find the antiderivative of. What's the antiderivative of e to the power of x cubed? The answer is we don't know. There are just functions out there that you cannot just integrate. And we have techniques for taking care of a lot of them, but we haven't techniques for taking care of all of them. So can you see why this being converted into polar as a technique is a godsend? I can't integrate this, but I can change it into another thing, which I can integrate. And therefore I still can get the answer. I just don't get it directly. I get it indirectly. Okay, we good with this one? Any questions for everyone?
Professor?
Yes.
Just in theory, you could also just solve that as a geometry problem, right?
What do you mean by putting it into some kind of software and just visualizing it?
Oh no, because it's a double integral. I'm sorry, never mind.
Yeah, it is a double integral. I mean, I could plug that in and see what it looks like. My gut feeling is it's probably going to look like some kind of hill, you know, surface. But in that itself, it's not particularly helpful. Okay, let's set up the next one. I won't necessarily do the whole thing this time. So the next one we're going to set up looks a bit like question 4. We're doing a double integral. And the function is that guy, which is not very pretty. And D is a semicircle. And it's working with the y-axis. Okay, let's draw that. It's a semicircle, radius 6. And if you do the y-axis, which is this guy, there's D. Are we okay with that? Now, if you don't recognize what that is, do you know you can just plug into Desmos and you'll see it? Now, I've just did a mistake here. Can anyone see my mistake?
Should we do oversight on the x-axis?
Yeah. Now, if I put that into Desmos, I would have seen it. So I guess the rule of that story is use Desmos. Right. Now, I want to describe this region in terms of r and theta, of course. Well, the radius part is 6, so I know it's going to go from 0 to 6. And the theta guy, yeah, you should have put it there. The theta guy, you're going to start by going this way, and then you're going to rotate, and you're going to finish that way, right? And I do remember talking about a simple shape like this yesterday. What's the start and finish theta to make this particular thing happen?
Half pi and 3 over pi.
We had that same mistake yesterday as well. Because a half pi to 3 over half pi will actually generate this side.
I think it was my mistake too. That's sad.
Well, you're allowed to do it 3 times, so that's only 2. So what's the correction then?
Minus half pi to half pi.
Agreed, right? Minus a half pi to there. So I can do theta equals negative a half pi to theta equals positive a half pi. I can do
Because the radius would be 6, either from -6 to 0 or from 0 to 6. That's why r is 0 to 6.
Yeah, if you imagine what the whole circle would be, it's 6. And it really doesn't matter which piece of the circle, the bottom half, the top half, the right half.
Okay.
It's still 6. So yes. Now, minus x squared minus y squared is minus r squared. Are you happy with if x squared plus y squared is r squared, this becomes negative r squared. We then have an r dr d theta. So that's our polar version of that double integral. This is separable. Okay, that guy there's dead easy. You want to trust me, but it ends up being pi. How am I going to do this, fella? Because this is where I'm about to stop. The integral from 0 to 6 of r e to the negative r squared dr.
U sub?
Correct. And that u sub, right? So dot, 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 dot. You got the rest.
Would the u sub be negative r squared or r squared?
It doesn't matter, both work. If you feel more comfortable, we can make it negative r squared, but r squared will work. So that's cosmetic, but yeah, I guess minus r squared might look slightly nicer. So if I'd thought about it, I would have chosen that one. If I'd chosen the r squared, all I would have got was 1/2 e to the negative u. And if you do it the other way, you get negative 1/2 e to the u. And both eventually, when you transfer back into the r's, end up being the same fella. So not so much a mistake as a choice that's mostly cosmetic. Are we good with that one? You could finish that one. Be comfortable with it. About to move it. Any problems? This is your chance to ask. Continuing. There we go. Let's show you some of the homework questions, what they look like, because I kind of do them cryptic. Right, that's the one that we just finished. There's at least a version of it, right? That's number 4. Can you see this one here? A double integral of the cosine of the square root of x squared plus y squared. D is a disk, which is just another way for saying a circle that's filled in. And there's no restriction, so that would be an entire circle, wouldn't it? So if I was looking at this piece, which describes what the region D is, it's a complete circle of radius 4. So R would go from 0 to 4, and theta would go from 0 to 2 pi. So there's my intervals. Wouldn't this fella here turn into the cosine of R? Right, because x squared plus y squared. And wouldn't you get this fella turn into an R dr d theta? So although I'm talking through this question, wouldn't this become R cosine R? And what technique do you use to integrate R cosine R with respect to R?
Integration by parts.
That's the integration by parts. If it had been like one of the earlier questions, R cos of R squared, it's a U sub. Do you see what a small difference can do to the method that you're going to use to integrate? Right, one could be a U sub. In this case, you would end up with an integration by parts. Okay, so here is the next one I want to do. It's going to be a version of question 6. And we are looking at a region D that's described as x squared plus y squared equals 4, which is circle, and its intersection with another region called x squared plus y squared equals 2x. Now, I don't see that as being something I would eat. Well, this piece here anyway, is something I would want to draw just off the top of my head. So I'm going to use Desmos. We got Desmos set up here. I don't know if I do. That's for later on. Okay, let's do Desmos. It's normally easy to find. There it is. Can you see Desmos? Can you see, I should say, Desmos now? Right. So what we're going to do with this fella is type in that information that was in those questions. So the first one, if I kick this little thing up, it might make my life easier. It's going to be x squared plus y squared, and it's going to equal 4, which is what we'd expect, right? A circle. And the second one is also an x squared plus y squared. But it's equal to 2x. Interesting. I have a quick look and make sure I wrote the thing down. Equals 4, where D is the region in the first coordinate that lies between the circles. Why does that not look right?
So you're integrating like a crescent moon shape?
Oh,
Yeah.
that's why I just didn't see it. Yes.
So we're just doing the first quadrant, so it looks like a edged
So
pie
it's-
shape almost.
Right. So if I go back and take everything, first quadrant. So
You're right, Brooke.
that, yeah, visually my brain just couldn't see that. I'm glad you noticed it. Right. So we're really only interested in, if I kind of stretch it to the point, there. We're really only interested in this funny little thing between the two, right? So it's up here. So I'm trying my best to draw something vaguely like that. And the key numbers here are 2. So I got my weird shape. Now I'm going to have to try and describe this weird shape in terms, this is my D, I'm going to try and describe it in terms of r and theta. If you are trying to think of a way of looking at this guy, you kind of come up and it kind of rotates around here. And I'm trying to take a typical line. Okay, so a radial line is what the fancy name is. Now, for this typical radial line, what's the range of r and what's the range of theta? Well, the range of r is going to be here to here. Agreed? Now, what do you know about this baby circle here, this baby half circle? What's its radius?
2x.
It's a number.
2.
No, what's its radius?
1.
1.
Right, this guy here. This guy here. So this radial line starts at a radius of 1 and finishes here, which is a radius of 2. So that's where my 1 and 2 came from. No, that's not right. That would be right if this was my center. All right. This
That
one's
felt weird.
caused this shape is causing me weird issues. So let me check something here. See what I'm not doing right. Ignore that, it's wrong. That would happen if you were looking like a shape like this. Right? That would be true, but that is not what's happening here. Something else is happening here. Trying to get back into Cengage because it's times me out, and I'm putting it on its solution to see what on earth is happening here, because I'm confused.
I think r would start at 0 and then go from 4 minus 2x.
Well, oh, you mean just describing it in terms of the relationships here?
Yeah.
Okay.
Because we're looking at the whole first quadrant.
Right. So if we do this guy, 2x is not going to be 2x anymore. 2x is going to be 2r cosine thetas. Okay, let's do it that way. So I've got the shape, but what I'm having trouble with is describing the range of r values. Now, on the furthest point, we're basically looking at an r value 2. So no matter what radial line I make, the end of it is definitely 2. So I'm comfortable on that side. If you look at this fella here, which is basically the equation of this half circle, r squared equals 2 r cosines. If you divide out one of the r's, that's the other guy.
Oh.
Yeah.
And theta is the easy one, 0 to pi upon 2. Darn
Professor,
it.
Professor,
Yes.
we can see your whole page.
Okay, let's show you it now. I got the little darling. Just wasn't thinking the right way. Right. If you take my radial line, you meet this guy first, and then you meet this guy second. And I'm taking this, these two equations, and I'm looking at them in terms of what the r values look like. This circle, the furthest away one is 2, which is what makes that happen. And this inside circle is basically r equals 2 cosine theta. So it means this distance to here is that, and that's what went there. So that's how I came out with the start and finish. The thetas were easy. To make this shape, the angle theta starts at 0 and it finishes at pi upon 2. And so I now have my region D. So I had to figure out what the distance from the origin to this semicircle is. And the way I did it is I found its equation in terms of r and theta and rearranged it so it became just r in terms of theta. And that told me that this distance is 2 cosine thetas. And then the big circle, that distance always has the same r, it's a 2. Right, double integral then is going to be from r equals 2 to r equals 2 cosine theta, and theta equals 0 to theta equals pi upon 2. And I've forgotten what the function was. And let's write it down. And the function that we're meant to be doing all this hard work to was x. So x, so I'll write it up here. It's double integral x dA. The x becomes r cosine theta. The dA becomes r dr d theta. So this guy is x. This guy is that. And these are d. Okay, let's make this look a little bit prettier. Now, I haven't mentioned it, so I'll mention it now. In the earlier questions that we've been doing, haven't we been able to do the r or the theta in any order we like, and it was because they were mixed? In this question, why does r have to happen before theta?
Because r is described in terms of theta.
Yeah, because of that, exactly. Secondly, because of that, this question is no longer variable separable, right? You can't separate it into two integrals. You have to do one followed by the other. Question?
On your integral, shouldn't it be 2 cosine theta? Because 2 cosine theta is the lower end of r to 2.
I think I've written 2 cosine theta. Where do you think I should be writing it?
Shouldn't it be isn't it the lower side of r?
Oh. Yes, and I did it here, but didn't translate it here.
Okay.
Yeah.
Okay.
Okay. I think my brain was got a little bit put out there, so let's just take this one to the end then. It's going to be theta equals 0. I'm just rewriting it again to make absolutely clear who we're doing and in what order we're doing it. Okay. If you integrate this expression with respect to r, you're basically just going to do a power rule to the r. So you're going to get 1/3 r cubed cosine theta, and then you're going to evaluate it at these two places. If you plug in 2, you're going to get 8/3 cosine theta. Take away that horrible mess. That's going to get you 8, so you're going to get 8/3. That's going to get you cos cubed plus another cosine, which is that fella. And you're here. Not the prettiest integral to do, and you do know how to do it, although it's probably, from Calc 2, it's probably one of the rarest types of questions that you've had to deal with. So what I would suggest you might want to do here is to do it as two separate questions. That's not variable separable. I'm just taking this guy and separating it from this one and subtracting them. And this I can do. This fella, I need to do on its own. I'll pull out the 8/3 because it's an ugly fraction, and just focus on how you would integrate that guy, in this case from 0 to pi upon 2. Any suggestions? How do you integrate an even power of cosine on its own?
You could do turn into a half angle.
Do we want to take one of those cosine squareds and change it into 1 minus sine squared?
In many situations, that's exactly what you would do, but only if it's cosine cubed, cosine 5 or 7. But when it's even cosine, the technique changes. I'm not sure what G means by the half angle. It may be correct, but I'm not sure what you mean by that. Tell me what I should write down, and then I'll understand what you're getting at.
It will be 1/2 of 1/2 plus 1/2 of cosine plus 1/2 of cosine 2 theta, the whole thing squared.
And I agree with you. Yes. Cos squared theta can be written as 1/2 1 plus the cosine of 2 theta. So cosine 4 is basically that guy squared. Now, that's going to get you 1/4 1 plus the cosine of 2 theta squared, d theta. I'm going to suck that quarter out because there's enough fractions going on right now, and that gets me 2/3. And I'm going to FOIL this out. And I now have reached this stage. Well, I can integrate one, I can integrate this fella. What am I going to do about cos squared 2 theta?
How did we get to 1/4 there?
1/2 squared is a quarter.
Ah,
What about cos squared 2 theta? I need to figure out something to turn it into, don't I?
The same thing.
Same thing, with an adaptation. It's 1/2 1 plus the cosine of how many theta?
4.
4. Gesundheit.
thanks.
Oh, you just sneezed twice.
I did.
We have a poem for sneezing in Britain. Do you know that this poem? Because it may have arrived in America.
No, what is it?
It's 1's a wish, 2's a kiss, 3's a disappointment, 4's a letter, and 5's something better.
So I'm up to a curse.
You're up to a kiss, not a curse.
Oh, okay.
So you can grab your boyfriend or whatever and tell him he owes you one. Okay, continuing. A half plus a half cosine of 4 theta d theta. This guy and this guy gets you 3/2. Got this fella, And finally, you've got this fella. You probably did not think that cosine to the power of 4 theta was going to end up being as ugly looking as that is. But that's pretty much all you can do. Now, at this point here, I think I'll take it one more stage and then just leave it. 3 upon 2 gets you 3 upon 2 theta. If you integrate 2 cosine 2 theta, you get technically 2 sine 2 theta with an extra half, so you just get the sine of 2 theta. And if you do this guy, you'll get a sine of 4 theta with another 1/4, which is why you've now got an 1/8 of them. Evaluated at theta equals 0 and theta equals pi upon 2. And I'm actually going to take it further. I was going to stop there, but I've just seen something kind of cool. You plug in pi upon 2, goes here. Won't that be the sine of pi? And won't that be the sine of 2 pi, which are all zeros? And if you plug in 0, you get 0, 0, and 0, so they're all zeros. So the answer is that that's the only thing that's not 0. Everything else is 0. Which, cancel, 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 cancel. Wow.
I got you. Yep.
A lot of work to find out a lot of zeros.
Yeah. Interesting. I mean, it definitely went wonky at the start. But I mean, I'm assuming that I didn't screw up anywhere, obviously. But pi upon 2 is actually quite an elegant answer for what was a really messy question. Are we good with that question? Going to move on? Okay. So we just have enough time to talk about what's going to happen tomorrow. We are still in polar form, but we are going to look at essentially the volume between 2 surfaces. So if you can imagine one surface intersecting in 3D space with another, you end up with an intersection region, right? A solid region that's the intersection of the first surface and it's inside the other one, right? It's a bit like the area between 2 curves in Calc 2, but it's the volume of a solid, which is the intersection of 2 surfaces. And that ends up being a double integral. And what I want to show you is an example of that. So here are 2 surfaces, and we are interested in how we could find the volume between the 2. So this time I'm using a different piece of software. The first surface is the square root of 9 take away x squared take away y squared. The second surface is x squared plus y squared. And these are the 2 surfaces. You see them? Now, if you look, it's a bit hard to see it, but can you see that one surface meets up with the other surface? Can you imagine then that there's a volume of intersection? Not an area of intersection, but a volume of intersection. And we would like to know what that volume is, right? What number it is. And so a double integral is going to do that. Now, what you have to do first is that somewhere on the floor, we need our region D. So I want you to imagine that these 2 curves intersect, and actually it comes out quite good. Would you agree that these 2 surfaces intersect on a circle? You can see the circle.
Yeah.
If you, the orientation I'm looking at is like we're floating above it, looking down towards the ground. So if you can imagine that hitting the floor, do you see that what you've got is a circle? So the region D is going to be whatever that circle is. And we'll figure out in a few moments from now how to get the equation of that circle, right? But we're interested in that circle, and that's going to get me my r equals 0 to 2, my theta from 0 to 2 pi, and that's the d. And then how do you get the other part? Well, let me show you now. Essentially, oops, let me write these two guys down before they disappear. So one of them is 9 squared y squared, and the other is x squared plus y squared. Okay. So let's return. And hopefully I've convinced you that when these two things intersect, they make a little circle, right? And you project the circle down onto the ground. And we now need to know what that circle looks like. Well, there's a generic version of it. Isn't the only thing I need to know is the radius? Right, let's see how that's going to work. If you want to know where this surface intersects with that one, don't you just set them equal to each other and solve? So I'm going to set this fella equal to this fella. And I'm going to do one of my favorite techniques for solving equations, and that is, as long as you do it to both sides, it's okay rule. So I'm going to square both sides.
So 9x squared minus x squared. So 9 is equal to, so 9½ is equal to x squared plus.
Agreed?
Yep.
Which is 9 over 2.
Is equal to x squared plus.
But isn't x squared plus thingy r squared? Remember, we're interested in the radius. In this case, the square root of 9/2 is my mystery radius. I won't call it that. I'll call it, I guess, 3 over root 2. If I want to be a purist, shouldn't I call it 3 root 2 over 2? So I know the radius. So the region D is going to be, using r and theta, r is going to go from 0 to that value, and theta, because it's an entire circle, is that guy. So that will be the D part. Now, how do we get the double integral that's going to give me my volume? Well, it's going to be this fella, right, the region D, of 1 r dr d theta. And the, oh, sorry, this fella isn't 1. This fella is this guy, take away that guy. So can you see this fella is going to be square root of 9 minus x squared minus y squared, take away square root of x squared plus y squared. And that's the guy. Now we already know what theta is, and we already know what r is. And this guy becomes 9 take away r squared, and this guy just becomes r. Takes a lot of writing this. Or the square root of 9 take away r squared minus r squared. Right, so this fella here is basically top surface take away bottom surface. Right, so whatever one of the two surfaces is higher up goes first, and you take away whatever one of the surfaces is below it. All right, so top surface, its equation, take away bottom surface. And that calculation will tell you the volume of the intersection surface, the intersection region. Right. don't have time to finish this, so only time to talk about it. Would you agree that we could do a variable separable? Oops.
Okay, I see what I missed out.
Question. Do we have a question, Jay?
Oh, no, sorry.
Okay.
Sorry.
So would you agree that I could do this as one and then just do this guy separately? Okay. How are you going to do r square root of r minus 9 minus r squared? How are you going to do that guy?
That's a U substitution.
Yeah, and that's just a power rule. You know, still take about another 10 minutes, but you would get it done at the end. Since this is a physical volume, right? It's a volume in three-dimensional space where the intersection of one surface meets up with another. It must be positive. So if you end up with a negative answer for whatever reason, either you just screwed up in your algebra, or maybe you switched places and you got them the wrong way around, right? You put the first one second and second one first. But it must be positive because it is a physical object. In this case, it would look something like that. It would actually look like an ice cream cone because that thing there is actually a cone. You know, that shape there is a cone. And this shape here is like a hat going that way. God, yeah, not doing well. But can you imagine the cone meeting up with the thing on the other side, and the intersection of the two looks a bit like that. See if I can make that happen. No, I can't. I guess if I change the transparency, you might have seen it in 3D plot, but not right now. Okay, say hi, everybody. We are good to go for today. And I'll hang about as always for any questions.
Thank you.
You're welcome. Tomorrow we'll do this. Bye-bye.
Take care.
You too. Bye-bye, Travis. Okay, I got some people still here.
Yeah, I have a question about one of the homework questions.
Okay, give me a... Is it something I can write down, or will I have to go looking for it?
It is in 15.1, and I just want to know basically if my setup was correct. I can share my screen if you want.
Yeah, let's do that. That seems to work quite well with you. So here we go. Right, it should be ready for you to share.
Okay. And now let me find where I did that, because I went on after messing it up. Okay, here we are. So it is the volume of the solid in the first octant divide.
I'm looking at your WebAssign homework. So you might want to scroll to the question you're talking about, and then I could read it.
Okay, it's question 14. And
I can see it. It's at the top. Okay.
Okay, perfect. So I figured out what the first octant was. That's just like, basically it's the first quadrant, except now we're in 3D and there's 8 octants.
Yes. Yeah, it's exactly what it is.
Okay, and we're bound, and I'm wondering if I'm screwing up my bounds, because I had the plane y equals 1 like that.
Correct.
And then the parabolic cylinder would be like that. And
that was your mistake.
Was that?
Yeah, rub out the parabolic curve that you put in. Right, z equals 25 minus x squared. If that had said y equals, what you've written was correct. But actually that just says z. So what you've got to imagine is what happens to that piece of information when you reach the floor, right? The xy plane.
Okay,
well,
and then
z is 0 when that happens.
So our plane is like down here.
Yeah.
And then these are hard to draw. The parabola is like, okay, hang on. I'm gonna attempt to portray that. So we've
All
got,
your parabola is going to do is intersect the x-axis at 5 and -5. So what you're going to create out of this is a rectangular region.
first, is it rectangular? Is it not like an arch like this?
In 3D space it is, but in 2D space, all that happens is that if you imagine the z being 0, you're left with 25 take away x squared, which means x squared will always be 25, which means x will always be 5 or -5.
And so
Those are the...
how do I describe that region then?
You describe it by going to the top picture and putting a little vertical line at -5 going up and a little vertical line at +5 going up. And that will create a rectangle. So y = 1 goes horizontal.
So that's going to be -5,
Uh-huh.
5. And then we're in the first octant. So really it's like only over here, right?
Yeah, and y = 1. So draw a horizontal line to finish the top of that shaded region. So now you're left with that little right-hand corner guy. So it's a 0 to 5, 0 to 1 guy.
Okay.
When the region z = 25 minus x squared, when it hits the floor, all you will see is a vertical line at x = 5 and a vertical line at 5. So you're now in the 2D plane. That's when the thing that, oh, I wish I could be with you right now. But you see that little archway that you're trying to draw? When that archway hits the floor, doesn't the only part that you see is a straight line at x = 5 and a straight line at -5?
You know, now that you put it like that, yeah, it makes sense. Definitely makes sense put that way.
Right. So what you're doing is you've got a 3-dimensional thing going on, but as far as the floor, the XY plane is concerned, things change when you're looking at from that perspective. If you looked at your shape from above downwards onto it, wouldn't you just see the ends of the curve, the 5 and -5?
If I was like hovering above it and looking down. Yeah,
Yes.
I do see what you mean there.
So that's kind of, your region's actually quite a nice region because it's rectangular, and rectangular tends to, you know, work easily. So you should be able to do a variable separable as well.
So wait, let me double check as well. As I've drawn that 3D that 3D thing, the
surface
would actually, yeah, the surface. The plane would actually be vertical, right? Is
what
that
plane
correct?
are we talking about?
The plane y = 1.
Okay, let me go into let me draw the thing for you in 3D and hopefully draw it well. Is it 3D plot? Try to find the right one here. Okay, 3D plot. 3D plot grapher, I think it's this one. Oh, darn it, I've got an installation version. I don't want the installation version, I want the online version. There we are, got it.
Should I stop my share for now?
Yeah, it'll take me just a few moments to put this fella in. I've got GeoBra 3D, so hopefully GeoBra 3D will handle that. I'm going to move over and show you what we've got to look at here. Right. Okay, I'm probably not the one I would want, but I've got something to play with. What's the equation? It was z equals?
Z equals 25 minus x squared.
Okay.
And then y = 1 for the plane.
Right, I'm not sure the y = 1 is going to be helpful, but I'll put it in anyway. Right, now, I'm going to shrink this darn thing up, but Yeah. Well, I guess if I shrink it more, eventually it'll meet. There we go. Okay, it's got really ugly orientation.
So the plane is vertical.
Right. So you can see the y equals is a vertical, right?
Yeah.
And you can also see the curved plane. But do you see that the curved plane, when it meets the floor, which is here, is two straight lines, one at -5 and the other at 5. Now, if I turn this guy and orientate it maybe this way, see, the scale's so horrible. Well, let's try it kind of side on. Can you see you get the y equal 5, and then you get the x equals 5 and -5, and that's where your rectangle is.